this lecture. Professor Debnath has done his master's from IIT Delhi in applied optics. He is electronics and communication engineer by undergraduate training, and then he did his PhD in physics from University of St Andrews, Scotland. Professor Debnath works in different optoelectronics platforms for applications toward energy efficient communication systems, renewable energy, quantum technology, etc. He is interested in on-chip optical communication, ultra-low power lasers, solar photovoltaics, quantum technology, 3D photonic crystals, and all this. He will deliver a workshop talk on numerical methods for optics and photonics. Professor Debnath, the stage is for you.
Okay, thank you, Professor Roy, for the introduction. So let me start. So this is slightly a bit different topic than has been going on in the today. So I work in this area of optics and photonics, and we do a lot of numerical studies with in this area. So as Professor Roy said, my work is mainly in designing development of different optical components for a variety of application, and we are particularly looking for on-chip optical systems. So the key material that we work is with silicon to make it compatible with the electronic side. We do work with other materials like graphene, and where the silicon does not work that well. So let me start by defining what is photonics. So in the area of photonics, we basically try to manipulate certain properties of light. So as you can find in Wikipedia, so it is the photonics is this research area where we generate, detect, manipulate, modulate light for different applications such as signal processing, amplification, switching, etc. So light has different properties, like it has power, it has phase, wavelength, polarization. So by manipulating all this, we are trying to apply in different different fields of application. So photonics, the name photonics came from photon, which is the smallest particle of light, and electronics. So the goal is to apply light for various applications where electronics had been dominating. So that is the goal. So replace electrons with photons. So this area is relatively new in comparison to other areas of research. So it started in 60s, 70s, around that time when laser was invented. It was invented by Theodore Maiman. So laser gives you this directional monochromatic light, which allows us to manipulate light in a more controlled manner to get certain applications. And along with the invention of laser, also low loss optical fiber was also proposed by Charles Cow around almost the same time. So the proposal is that by using dielectric waveguide, you can transmit information loss-free. Okay. So after 70, 80 years now, where we are. So now photonics has application in various fields, for example, in communication. So nowadays, all communication are based on light. All the telecommunication, metro level network, everything is based on light. Then we have renewable energy, solar photovoltaics, solar cells. These are all manipulation or controlling light or light matter interaction. Then we have autonomous vehicle where we use LiDAR, light detector ranging. So there also we use some sort of photonic structures. Then we have optical sensing, IR gas sensing. Then we can see LED display devices. These are all comes under the realm of optics and photonics. Then we have material processing like laser cutting, laser welding, Interestingly, this is the major area where laser is being used commercially or industrially. Then we have metamaterial, which here we are going towards more into the research domain. The commercial aspect of it has not still been full grown. Meta lenses, like flat lenses, we can design with photonic manipulation. Then we have invisibility cloak, if someone is interested. Then we have one of the area which is growing quite fast is this computation, all optical computation, and main application of all optical computation is in quantum computation, quantum computers, quantum communication. In that regard, photons has certain advantage over electron-based quantum computation. So you, rather than using electron as the qubit, we in this area we use photon as the qubits. So now one of the major area which is where the photonics is growing, the research and the development of photonics is growing is in the data communication. So this picture is a picture of a data center where we have hundreds and thousands of racks sitting next to each other. Now, what happens is that because of the increase in the demand for bandwidth, information bandwidth, we can no longer use metal-based interconnections like coaxial cables. They become too lossy. So what we do is we replace those metal-based interconnects using what is known as active optical cable. So if you look at these are optical fibers, and at the end we have what is known as optical transceiver. So the data that comes out of these racks, electrical form, they get converted into optical signal, gets propagated through this optical fiber, and at the end, the receiver, which then converts the optical signal back to electrical signal and goes to for further processing. So now what is happening is that the optical communication now, this optical communication is, it has been used for telecommunication for now many decades. It has also penetrated into metro network, 10 kilometer, even in the data center, as I just have shown you. Nowadays, in what our research is, we are even trying to go further into the chip. That is, we are trying to approach as close as possible to the transistors. For all the communication, we are trying to implement optical communication. Now, so in order to achieve that, there are different components. Say, for example, we have light sources, we have modulators, photodetectors, then we have routing. We need to route the light around the circuit, photonic circuit. So there are a lot of components that we need to develop. Now, unlike electronics, the photonics or optoelectronics, if we want to generalize it, the components are not yet standardized like the electronics counterparts. So both in academia as well as in industry, there is still research going on in terms of design development of devices, improvement and increasing the efficiency of the devices. So for that, what we need is we need some reliable and fast analytical and numerical methods to design such components. So this is where the numerical methods, analytical and numerical methods in optics comes into play. So before I go into different numerical methods, let me just introduce in a very short span of time what is light and how do we handle analysis of light. So as most of you know, light has a dual nature. So it behaves as wave. Sometimes it also behaves as particle. So it has a wave particle duality. Now, if you look at the wave nature of light, light is an electromagnetic wave. So it has electric field and magnetic field. So since it's a wave, there is a frequency associated with it, there is a wavelength associated with it, and the product of these two gives you the speed of light. It also has polarization associated with it. How this electric field is oscillating, what is the direction of oscillation, so and so. Now, light also has a different property. Depending on how we measure light, or the property changes. So light also has the particle nature. That is, light is considered as, can be considered as the flux of photons. And photon means the smallest energy that can be, that we can measure. Okay. So each photon has certain energy, and that is given by, that is proportional to the frequency of that light. Say, for example, green light has higher energy. The green light, the photon of green light will have higher energy than the photon of red light. Now, I want to analyze or simulate a certain photonic system. Either we can go for wave model or we can go for photon model. Now, the way I understand it and the way we can differentiate whether we need to go for a photon model of light or wave model of light depends on whether the process, that is when light is interacting with the matter, whether that process gives any, if there is any energy transfer of energy from the light to the matter or matter to the light. That tells us whether we go for a wave model or photon model. So in most of the cases, say for example, free space propagation. I think someone's mic is on. Okay, thank you. So we go for wave model when we have, let's say, free space propagation of light or guiding of light. That is, light is guided through optical fiber. We want to analyze it or we want to model it. Or say, for example, scattering from some nanoparticles or storage of light using some optical cavity, or let's say some focusing using lenses. So it's basically phase front shaping. So all these processes, there is no transfer of energy from the light to the matter. So in that case, we can simply use the electromagnetic model of light, that is the wave model of light. Now, in case of when the interaction happens, during the interaction, if the energy has been transferred, say for example, in case of a photoelectric effect, when the light falls onto a metal, if the frequency is above certain energy level, what will happen, that the electrons will come off the metal. So in that case, the energy is being transferred from the light to the matter. In that case, we can no longer use the classical electromagnetism to explain this phenomenon or to model this phenomenon. Now, in case of a photonics research, in most of the cases, what we see is that we can very well understand the system by simply using the the theory of classical electromagnetism. We do not need to go into the photon model of light. Okay. And say, for example, if we want to design a waveguide, or if you want to design a cavity, if we want to design a lens, so on and so forth. In all the cases, there is no transfer of energy. So in that case, you simply use the wave model of light to analyze. And for all the classical electromagnetism, there are 4 equations given by Maxwell. So those 4 equations are sufficient to understand any photonic system. So if you look at in time domain, the equations are given like this: del dot D equal to rho V. Rho V is the free charge. Then we have del dot B equal to 0. These are this is Gauss's law. This is Gauss's law for electromagnetism. Then we have curl of E del B by del T. That gives you that is coming from the Faraday's law. Then we have Ampere's law. So this is in time domain. We can have 4 equations in the frequency domain as well for individual time harmonics. So depending on the model that we choose for numerical analysis, whether we go for a time domain modeling or frequency domain modeling, we'll choose either of these 2. And along with, there is a constitutive equation. So these equations are necessary to see the interaction between light and matter. So this is all these parameters are associated with the wave, D, B, E, H, whereas epsilon, mu, the permittivity, permeability, these are all associated with the matter. So combining this constitutive equation along with the four Maxwell's equation gives us a complete picture how light is interacting with a certain matter, either metal or dielectric. Now, when we use Maxwell's equation in optics or photonics devices, what we often come around is that the material that we choose for optical or photonic devices are dielectric in nature. What it means is that there are no free charges. So Maxwell's equations, along with the constitutive equations, simplifies a little bit. So we have the rho v becomes 0, there is no free charge, there is no current, and usually we do not use any magnetic material. So mu becomes mu naught, that is free space permeability. So now if we look at the two Carl equations, from that, if we look at in free space, that means the light is propagating simply in vacuum. In that case, these two equations, if I combine these two, we get a decoupled equation, which gives you a form of a wave equation. So we can solve it to find what is how the electric field is propagating as well as how the magnetic field is propagating. Okay, so in case of a free space, free space or a bulk medium, the solution of this always becomes a plane wave. Okay, but when you have a bounded medium or a periodic medium, then the solution becomes more complex. Now, along with those Maxwell's four equations, we also need the boundary conditions, what we call as the physical boundary condition. So if we are interested in dielectric interfaces, then the tangential components of electric and magnetic fields, they become continuous. The normal components of the flux densities become continuous. And if a wave is propagating, then the tangential component of wave becomes continuous at the interface. Now, with this boundary conditions, along with the four Maxwell's equation, we can analytically or numerically solve almost any problem of electromagnetism, as long as there is no transfer of energies involved. If we are still in the domain of classical electrodynamics, only by using those four equations along with the boundary conditions, we can solve any problem. Before we go into the different numerical problems, I just want to mention a distinction between optics and photonics. Now, the light matter interaction, although I'm saying the photonics, the area of photonics is relatively new, but the light matter interaction is not new, and we have been manipulating light with matter for centuries now. Right. Now, the distinction comes from the fact that in optics, the structures that we deal with are much larger in dimension than the wavelength of light. Say, for example, if we are designing a lens, so lenses are typically the size of a couple of centimeters. Whereas if I am designing a lens for optical frequency, that is wavelength, let's say green light, so which is 500 nanometer. So there is a huge difference between the wavelength of light that we are trying to manipulate with the structure that we are using to manipulate the light wave. So in that case, that comes under the realm of what we know as optics. Whereas in photonics, the structures that we are using to manipulate light are either of the same dimension or smaller than the wavelength of light. Say, for example, optical fiber. Now, optical fiber, if I look at the length of an optical fiber, it can be a couple of kilometers. Right. But if I look at the cross section, the critical dimension of the cross section is in micrometer. So, for example, if we look at the fibers that we use for telecommunication, the core diameter is only 9 micron, whereas the light that we have allowed to propagate through the optical fiber is around 1.5 micron. So the dimension of the structure that we are using to manipulate the light and the wavelength of the light itself is of similar order. So in that case, we can no longer use a simplified version of the property of light. So in case of an optics, what we do is we treat all the fields as scalar quantities. There where the approximation is allowed, even if we do certain approximation, even if we consider the light as not an electromagnetic wave, but certain rays, certain straight lines going in straight direction, we can model or simulate those structures quite accurately. So for that we have, so when we are talking about optics, we can use the geometric theory of reflection, and we can use what is known as a ray tracing method to perfectly predict what will be the behavior of a, let's say, for example, a lens. Whereas in photonics, the light, since the structure is very comparable to the size of the wavelength, we can no longer use that approximation. The approximation will not be valid anymore. So you need to use all the wave properties of light, such as polarization, the direction of that vector nature of the electric field, magnetic field altogether, and then come up with some numerical methods. So there are many methods available. Some are good for some simulations, some are good for other simulations. But here I have noted some of the most commonly used methods. Simulation, semi-analytical, some of them are semi-analytical, some of them are purely numerical methods. So we have transfer matrix method, we have rigorous coupled wave analysis, plane wave expansion method, finite element method, then finite difference time domain method, finite difference frequency domain. These are very commonly used numerical methods for simulating optical and photonic structures. So since we have a limited time, I will not go into details of all of them. So I'll just pick 3 and then quickly introduce you to these methods. And coincidentally, these methods we also use regularly in our research. So now transformatic method, this method is used to analyze layered structures. As I mentioned earlier, we use different methods for different specific tasks. So transformatic method works very well when we have a layered medium to simulate. Say, for example, layered medium, we can think of anti-reflection coating on your optical glasses that we wear, eyeglasses. We use transformatic method for dielectric mirrors. So transformatic method is a frequency domain method. Okay, so let me just give an example. So let's say I have a anti-reflection coating on a eyeglass. Now what it is actually, we have a thin layer of dielectric, that is transparent material on glass. Now the way we choose that thickness is, say suppose I want all the light to pass through the structure. So what I will do, I will choose that thickness such that the reflection from each of this interface will cancel each other. There will be a destructive interference between the wave that is reflected from this interface and the light that is reflected from this interface, and they destructively interfere. And thereby all the light will simply pass through the glass. So this kind of structures can very easily model using transfer matrix method. And there is another design, which is structure, which is very common in photonics and optical devices, which is called a dielectric mirror. So when we go for on-chip photonics or integrated photonic circuits, we do not use metal mirrors as we use day-to-day life, because metal mirrors are very lossy. Most of the huge part of your light that falls onto a metal mirror gets absorbed by the metal itself. So what we do instead is we use dielectric mirror, so which is a periodic layers of transparent material. Okay, so what happens is that when the light falls, the light will be reflected from each interface Now we designed this such a way for a particular wavelength of our choice. All the light that is reflected will interfere constructively rather than destructively. So as a result, the reflected light gets built up and the transmitted light reduces in terms of intensity. So after a couple of bilayers, what you will end up with, no transmitted light at that particular wavelength, and all the light will be reflected back. And it gives you almost lossless reflection. So how does it work? So let's take 4 layers of dielectric, let's say refractive index N1, N2, N3, N4. Now let's say the light is incident on this side and the light will be transmitted and some light will be reflected. Now if I look at it and try to solve it analytically, what you will see that there are 5 transmissions that I need to take into account and 5 reflections that I need to take into account together. So this becomes quite complicated to handle. So what we do instead is, if we suppose we know the field distribution at the input, let's say plane wave or something. In this case, it's not a plane wave, but let's say we have a uniform plane wave. So what we will do, instead of considering all the layers together, we will use one at a time. And we are doing everything in frequency domain, that is a single frequency, and then we are doing this analysis. So we will then calculate what will be the field distribution after one layer. Okay. The way we are calculating, then we find a transfer matrix, and this coefficient of this matrix can simply be calculated by using the boundary conditions that we discussed earlier. But if you are interested only in the reflected light or transmitted light, we can use the Fresnel equation to get these parameters. Now we can do this for individual layers one by one, like this, and then the 4th layer. Now once we have all this information, all these matrices, since it's frequency domain, we can simply make it the product, and that gives me the relationship between what is the field distribution here and what is the field distribution here. And this is what we call as a global transfer matrix. So now we know what will be the relationship between input field and the output field, and thereby we can estimate what will be the transmission spectra, what will be the reflection spectra, what will be the field distribution, so on and so forth. It's an experimental study that we had done recently. So you have 6 bilayers of silicon dioxide, that is glass, and titanium. 6 bilayers here, 6 bilayers here, and there is what is known as a cavity with a different thickness of SiO2. Now if you look at the experimental comparison with experimental and simulation, you can see that the dashed line is the numerical simulation that is done with transfer matrix method. And this is the experimental result. So transfer matrix method works quite well when you have this kind of structure, layered structure, where all the in other directions, in this direction, lateral direction, it is considered to be infinitely extended. So just some of the benefits is this: very simple to implement. It is quite stable. It does not have any instability issue. It's very fast as well as efficient. The main problem is that it is limited to a certain kind of devices only, that is layered structures. And also it is, since it is a frequency domain method, it is not suitable for transient analysis. Let's say I want to see how an optical pulse is propagating through a multi-layer structure. This will be difficult to will be difficult to implement using transfer matrix method. The next topic that simulation method that I want to talk about is plane wave expansion method. So plane wave expansion method, actually we have taken this algorithm from electronics. So in electronics we have semiconductors. Semiconductors are nothing but some periodic crystals. So the way we study the electron behavior in a periodic crystal, we have taken the same concept for photonics. So plane wave expansion method is very popular among photonic crystal community. So what it does, it gives you the how electromagnetic wave, electric field, magnetic field, how they propagate through a periodic lattice of dielectric material. That means periodic lattice, when I say periodic lattice, I mean, say this is a refractive index N1, this is refractive index N2, N1, N2, N1, this is a 1D photonic crystal, 1D periodic lattice. This is a 2D periodic lattice, and this is a 3D periodic lattice. So the light behaves quite interestingly in these kind of periodic structures. The same way electron behaves in semiconductor. So this plane wave expansion method is used to analyze how does the dispersion relationship of light behaves in a periodic structure called photonic crystal. And it is a Fourier space method. That means both the electric field distribution as well as the material parameters, all of them are converted into Fourier space, and then we do the analysis. Okay, so now, as I discussed, photonic crystal, it bears some resemblance with semiconductors. So what happens is that it has a band gap. That means a certain range of frequency within which the light cannot pass through that structure. So within the band gap, wherever you want to shine light, want to send light, the light will not pass through it. And it has tremendous potential for various applications. So for example, nonlinear photonics, that means second harmonic generation, third harmonic generation, we can do very efficiently. We can get lasers with a very, very low threshold current. Then it has application in integrated photonics. It has application in quantum computation through quantum electrodynamics. And this is something which is commercially available photonic crystal fibers, which gives you better performance in comparison to its counterpart, flat step index fiber. Now, if we want to look at the field distribution of a photonic crystal structure, I'm taking as a 3D photonic crystal structure. So we have our well-known curl equations. These are all used in frequency domain. Now we are converted into frequency domain. This is the Faraday's law. This is the Ampere's law. So we have put both of them in frequency domain, and then when we combine them, we get a wave equation. Now in case of a free space, this epsilon r is nothing but 1. So this converts into a well-known wave equation with the solution of which is a plane wave. But since this is a periodic structure, so this is also a periodic function of space. So as a result, we need to solve it differently to get all the field distribution inside this structure. Okay, and if you look at it, so this equation has a solution which are known as block waves, similar to block waves. If someone is familiar with semiconductor physics, the block waves that we get in periodic potential for electrons. So the field distribution takes the form of the periodic envelopes. It takes the form of a plane wave with a periodic envelope onto it, and this periodic envelope has the same periodicity as the period of the structure. So if I look at just the equation, it's essentially an eigenvalue problem. Okay, and using plane wave expansion method, we solve it to get the eigenvalue, which is the wavelength, and eigenvector, which is the field distribution for different propagation constant. This is, we have developed one structure, 3D photonic crystal structure, and here one of my students got this quite nice band gap effect in a 3D photonic crystal. So just to give you an insight, so this wave, this frequency from this point to this point, any frequency, if I want to send light through this structure, it will not propagate through it. Now imagine if I have a structure which is everywhere except at the center I have some defect, and then I put this frequency somehow, and that frequency will have nowhere to go. So photonic crystal has application in energy storage, like storage of light and all that. So using plane wave expansion method, we can we can find this dispersion relationship. We can find the field distribution at different points, different frequencies with different propagation constant. Now, there are certain benefits of plane wave expansion.
Professor Debnath, somehow the slides are not visible.
Why is it gone again?
I can see a whiteboard instead.
Huh? What? How did it come? No, it's gone actually. When did it?
You have to reshare it probably.
Okay, is it now?
Yeah.
Where,
so somebody else must have. Participants,
Yes.
please do not try to share the screen. Some participant has taken the control. Okay, please go ahead.
So
please go ahead.
okay, I think I'm not sure where.
I think again somebody else is Palash Ghosh. Palash Ghosh, please maintain the decorum. Yes, it is visible.
I can still see some slide being shared.
Somebody is trying to do it. I'll do something, but you please go ahead.
Yeah. Okay. 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 So this plane wave expansion method is also very specific to a certain devices. Certain type of devices. In this case, some periodic structure. Plane wave expansion method works quite well. But it is not useful if we want to say, for example, simulate a structure which is metallic in nature. So plane wave expansion method does not work in that case. Or also if it is
again, Palash Ghosh. Yes, go ahead.
Yeah.
Somebody named Palash Ghosh somehow is sharing his screen. Please do not do that. Disturbing the entire lecture. Please go ahead.
All right. So now I'll talk about one simulation method in optics and photonics, which I think can do almost every simulation that we can think of. That is called finite difference time domain method. So finite difference time domain method is used in RF microwave research as well. In photonics also we optical and photonics domain also we use it quite regularly. So this method was first proposed by Yee in 1960, around the same time when laser and this optical fiber were invented. So finite difference time domain method, or FDTD, it is a finite difference method to solve the Maxwell's equation. So this is, in a way, this is the most realistic and intuitive simulation. It is a brute force way of simulating. So what you see, what you simulate. Okay, so it can simulate any structure, big, small, no matter, periodic, aperiodic. So here you can see I've just simulated one light propagating through some structure. Okay, so the advantage of this method is that it records the movement of electromagnetic wave in a dynamic way. It records like a movie. So it is good for simulating dielectric structures, metallic structures. It is good for if you want to do nonlinear simulation, linear simulation. It is also good for transient analysis. Let's say if you have an optical pulse, laser pulse, how laser pulse propagates through certain medium. If you want to simulate, FDTD is I think the best way to go forward. So I'll just give a broad description on FDTD and how it works, just the very basic. So if we suppose we have a simulation domain where we have different refractive indices, and we want to simulate how the electromagnetic wave evolves in this medium. So what we have is at every point, if we have an electromagnetic wave or light propagating through the system, at every point we have this relationship. A time varying magnetic field gives a circulating electric field. A time varying electric field gives a circulating magnetic field. So this is happening at every point, and these are happening simultaneously. Now in FDTD, what we do is first we split it into grids, right? Cartesian grids, and we can use different boundary conditions. Here I am just showing a perfect mesh layer. We can use a periodic boundary condition. We can use block boundary conditions, so on and so forth. So once we discretize it, then we calculate the electric field and magnetic fields at discrete points rather than calculating electric field and magnetic field everywhere, which is not possible computationally. What we rather do is calculate electric field and magnetic field at discrete locations. Okay, and then we evolve this electric field and magnetic field at every grid as we increase the time. So this is how we are doing it. So this is the closest to reality what can happen in an actual device. So in simulation, what we rather do in reality, what happens, this electric field and magnetic field are coupled in a continuous, in a simultaneous way. Electric field changes magnetic field changes electric field. But here what happens is that in simulation, what we do, we first get the electric field. I think there is some mistake here. No, that is fine. So we get the electric field from the magnetic field, and then we go to we get the magnetic field from the magnetic field flux density. Then we go for the electric field from the magnetic field, and then go on. So rather than doing it simultaneously, rather than finding the electric field and magnetic field simultaneously, we do it sequentially in FDTD. And the way we solve this differential equation, so this is, let's say if I take this equation, there are 4 variables, right? X, Y, Z, special variables, and one temporal variable T. So we need to solve this equation by using finite difference method for all the different variables, that is X, Y, Z, and T. So this is a simplified flowchart of FDTD algorithm, which is also known as Yee algorithm. So we start by considering all the grids has 0 electric field and magnetic field. Then we start first by updating D, that is the electric flux density from the magnetic field. Then we update the electric field from the flux density. Then we define or handle the boundary conditions. We also handle the source, because if there is no source electric field, then whatever we do, the electric field and magnetic field will always be 0. So we do that. Then we go to updating the magnetic flux density from the electric field. Then we go to magnetic field from the flux density. Then we handle the boundaries. Then if there is any magnetic field source, so some sources we can think of as, let's say, dipoles. Okay. Electric dipole or magnetic dipole. So this is done in a single time step, and then we increase the time and repeat the process over and over again. Okay. So with that, if we look at a single time step, what we end up with is since we are not calculating electric field everywhere within the grid, so for each time step, for each grid, we have single electric field or magnetic field. Okay, and then we do some interpolation to get a distribution or a sense of electric field distribution or magnetic field distribution in the simulation domain. And that is done for each time step. Okay, and we record this information one after another. Every time step we record these informations. So this is in a nutshell what FDTD algorithm is. Okay, so now as I said, FDTD algorithm can be used for almost every possible scenario in optics and photonics. But one of the problems that we face is that it is not very good for curved surfaces. This is where I think finite element method works better when we go for a curved surface. Since we are using only Cartesian grid system, that is either we have squares or rectangles. If we have curved surface, let's say we have a curved surface here. Now, if we want to grid it, so these are the discretization errors that we will have at the boundaries. So FDTD algorithm suffers in that regard. Yeah. So one way to solve this is by simply increasing the number of unit cells. Yeah. So one of the problem with that is that you need more simulation time. Okay. So now, just to give some idea of available resources for doing computation in photonics and optics. So for finite different time domain method, we have several commercially available and free softwares. Say Numerical, which is now under NSYS, and then we have Artsoft, then CST. All of them are quite well, and we particularly use Numerical quite regularly. Then we have a free software from MIT, which is known as MEEP. So all of them you can use for simulating photonic and optical structures using FDTD. And there are other COMSOL, obviously, if we want to use finite element method, we go for COMSOL. Then if we are simulating, say, photonic crystal structures, we go for, again, Artsoft has a plane wave expansion method module, and then MPB from the same group, MIT group, which is a free software. Of course, if you do not want to go for available softwares, you can always simulate everything using MATLAB. Okay. Now, since this workshop is about HPC, I thought I'll just give you some reason why we need HPC in photonic simulation. So HPC will be useful when we are going for complex photonic systems. Just one point that FDTD is, I mean, HPC would be quite useful for FDTD. We can have that the splitting of this concurrent simulation and others. So HPC will be good for FDTD based simulations. So now, if we want to simulate complex photonic structure using FDTD, as it is time domain dependent, as well as especially we are simulating. So if the structure becomes big, the simulation time becomes extremely prohibitively high. And then we have meta surfaces. So if we have some sort of periodicity in our structure, it is easy to simulate with periodic boundary conditions. But when we do not have any periodicity, if we have a random structure, in that case, simulation time becomes very large. Okay, and then we have optimization problems, such as solar cell optimization problems. Then we have integrated circuits optimization problems. So this is an example. So this is a grating coupler. This is to couple light using optical fiber into an integrated circuit. So depending on the spacing between these ridges and what is the height of these ridges, the coupling, we can optimize the coupling. So this kind of optimization problem, for example, photonic crystal cavity. So if we want to increase the quality factor of a photonic crystal cavity, we need to do optimization of these structures. So this kind of optimization problem can be very, I mean, HPC can be very useful for this kind of problem. Otherwise, the time taken becomes prohibitively large. Another area that photonics is gaining interest is neural network, all optical photonic neural network. So there are some interesting results recently coming out where we use some diffractive optical elements to do classical classification. So this is an example where they managed to classify written digits. Okay. So this kind of simulation, which requires a huge computational power. So here, this is another example where we are using photonic neural network using integrated circuit. So the designing of these kind of structures require huge computational power, and I think where HPC will be quite useful. So okay, with that, I would like to thank you for listening. And yeah, if you have any question, I'm happy to answer.
Thank you, Professor Debnath, for explaining the basics and then also explaining the numerical methods in photonics. I think for some of the participants, this is a new field, and for
Yes.
some of them, yes,
Yes, I know.
for some of them, it's who are working on it, they will also be greatly benefited. So I can see Saurabh Tripathi has raised his hand. Mr. Tripathi, if you can ask your question.
Yes, sir. Thank you. Sir, I want, Kapil sir, I want to ask you whether there are some open source software for numerical technique that you told under the header optics, such as ray tracing and uh,
Ray
ray
tracing,
tracings. Yes, sir.
mm, that I'm not sure because I do not work in that area. But Zemax is there, but it is not free, of course. Uh, um, Sorry, I cannot
So
answer. Yeah, I do not have
yes,
that.
sir. So can this ray tracing technique be implemented? Can it be implemented in MATLAB or some
Yes, you can.
anything?
I think you can implement. It is just so ray tracing basically. I mean, I'm just speaking top of my head. If ray tracing simply uses your Snell's law, right?
Yes,
So
sir. Snell's law
Snell's
applies.
law. So if you have, let's say, if you know the refractive index of the material for different wavelengths, that means if you know the dispersion of that material, you can use MATLAB in principle. Yes, but I've not done that myself. Sorry.
Okay, sir. Fine. Fine, sir. Thank you.
Yes, anybody else? So, I mean, I have a question which may not be very relevant to, but these computations usually how expensive are they? What type of platforms, resources do you need for this?
So at the moment we use desktop with 64 GB RAM, and we can do simple simulation, but it scales up very quickly as soon as you, let's say, go from a 2D simulation is very quick, but as soon as you go for a 3D simulation, it becomes quite I mean time consuming. Uh, so again, depending on what type of simulation we are doing. So for example, some of the simulation which we FDTD that I discussed may take a day, whereas if I do the same simulation with FEM in console, it may take within an hour it will complete. So
But
we,
what
we,
will
we
be what will be the accuracy?
accuracy will be good. It all depends on what is the requirement. If, say, for example, FDTD works best when I have a FEM works best when I have a resonating structure. So when I have a single frequency. In that case, FEM works quite well and it works quite fast. Whereas when I have some time, when I have a broadband signal, let's say optical pulse, which if I look at the frequency spectrum, it will be quite broad. In that case, FEM will be very time consuming, FDTD will be quicker, relatively quicker. So it is always depending on the requirement. But so there are limitations of FEM, but in terms of what we can simulate or what we cannot simulate, FDTD does not have that restriction. The only restriction comes from the fact that how much time we can spend. So yeah, that's what I think. Yeah.
Okay, okay, okay. So if nobody else has any further question, then let's thank the speaker. Thank you,
Okay.
Professor Debnath.
Thank you.
And we'll see you again tomorrow in the panel discussion.
Yeah, sure. Thank you.
And 4 p.m. So participants, we are done for today's session. And today by evening, you should receive an email in your registered mail address regarding the feedback form. You need to fill up the feedback form for this workshop, and your certificate, etc.